boiling the water will have a combined effect. If you don't boil water, then the tea powder will not have a combined effect, right? You understand? So there are the factors which will have a combined effect, which will have an interaction, and which will have a interaction effect. And there are some factors which don't interact and which will have some independent effect. Okay. So example is like you can take a simple example. And in the BTech first year, since as I said, it is an interdisciplinary work. In the BTech first year, probably everyone might have done machining on lathe machine, right? In your mechanical workshop, you might have worked on lathe machine and machining of lathe machine. So if you remember once, so generally the workshop foreman will give you a cylindrical job and he will ask you to machine it, right? He will ask you to machine it. So what are the factors that influencing that machining? So if you remember, the rotation of the workpiece of a lathe machine is one of the factor. So what is the RPM you are using there? And you will touch the, say this is a cylindrical workpiece, and we will use some cutting tool, right, in the lathe machine, and we give some feed motion to cutting tool. So that is also one of the parameter. So this rotation in RPM is also one of the parameter, and the depth of cut. In order to remove this surface, we give some depth of cut. So that is also one of the parameter. So these three are the factors, independent factors. And what is the response? So the reducing the diameter means the dimensional accuracy is the response, and as well as, say for example, the surface finish obtained of a given job is also one of the response. So based on your different strategy, you need to understand what are the known factors, unknown factors, etc. And accordingly, you can decide. You can decide the strategy. You can decide the strategy of the experiment. You need to see whether you are getting a curvature or not. So if the curvature is there, then it means that the solution is getting optimum. Okay, the solution is like, means the results are increasing, following increasing trend, and then it is reaching at certain point optimum, and then it is following the decreasing trend, right? So you need to think about the curvature of the results and the parameters obtained, and then at that stage actually you can stop the experiment, because if you increase further the parameters on x-axis and y-axis, you may not see the fruitful results, because already it's following an increasing and decreasing trend. So you need to look into those factors also when you're designing the experiments. Yeah. So response surface methodology basically it resolve around the assumptions that the response is the function of set of independent design variables. So these x1, x2, x3, xk are the independent variables. Function can be approximated in the some region of polynomial model. So y is equal to f of xi, y is equal to f of x1, x2, xk. So here the y is the response variable which depends upon this x1, x2 and up to xk independent variables. Yeah. So here you can also find out that the factors are given the first order equation and also the second order equation in order to find out the best solution by using the response surface methodology. So this slide will gives you the background of response surface methodology, first order and second order. Generally, we consider when we are doing the optimization, we consider this y is equal to f of x as an objective function. So once you have an objective function, then you can play a lot of number game, you can incorporate a lot of statistical techniques, mathematical models, etc. in order to do the optimization. Yeah. So independent variables and dependent variables. So we have already discussed with an example. So once again, here we'll see independent or input variables are those factors which are at control for the experimenter. So this point to be noted. So these are the factors which are at control for the experimenter. Dependent variables are not at control of the experimenter. So these factors are varied in an accepted limits to identify the response it makes on the dependent variable. So dependent variables are not in control of the experimenter, but however, these are in the control of the independent variables which are varying. So you need to plan the independent variables in such a way that your dependent variable is also under your control. Yeah. So in continuation to the polynomial equation, so here we are adding some epsilon here. So this is an error. So why error is considered is consider any dependent variable y. So this is the dependent variable, and there is a set of input variables like x1, x2, x3. Like these are y is dependent and x1, x2, xk are the independent, which have control to the experimenter, and f of the function we are adding. And the point here is when the underlying mechanism is not fully understood. So if you are working on some experiments and when you are apply this response surface methodology and when you are finding the objective function, when it is not fully understood, then the experimenter must approximate the unknown factor f with an approximate empirical model error. So that epsilon is the error. So these kind of objective functions we need to generate first before going to the optimization. So experimental methods and how do we validate? So there are various theories, various concepts to validate the experimental methods. So validation of the model can be done by the experimental method by testing the sample in the design space and by matching the observed value and the predicted value, etc. Right? So whenever you purchase any instrument, generally they will give a sample that is the observed value or the standard value they will give, and you need to perform the experiment and you need to check. Just for a simple understanding, if you buy a thermometer, if you buy a simple thermometer, then they will give you the calibration value. They will give you the value, and you need to reach that particular value, right? Then only your instrument is working. Otherwise, you can assume that your instrument is having some error. And what is that error? You need to find out, and you need to add that error if you want to reuse that instrument. Otherwise, you need to go for another instrument. So there are various methods to validate. So you can directly test the sample by using the sample already available, or there are some statistical methods which we use to validate our experiments like p value, r square value, f value, etc. by comparing. So this will not go in deep. Our interest is to find out the experiments and then to find out the regression analysis equations and then how we have done optimization and how we improve the process of the better, which is better than the existing process. So why we do experiments? So to obtain maximum information from minimum number of experiments. So generally we design the experiments to find out the maximum information from minimum number of experiments. To screen factors when large number of factors are present. So there are various factors, like I have shown you one equation, y is equal to f of x1, x2 up to xk. So there are large number of factors involving, and when you perform the experiments, you will understand which are important, which are having more influence and which are not having the more influence. You can take any kind of example. Sometimes the climatic conditions will play an important role. So if the climate is too hot when you are doing experiment, then there is a chance of getting an error, any kind of experiment. And when the person who is doing experiment is not skilled, then there is a chance of some doing mistake, right? In that case also the factors will vary. But if you perform more number of experiments, for maximum information, then you will understand what is the factors and their result, etc. So based on that, you will get an idea. And what are the softwares we generally use to conduct the design of experiments? Like Design Expert is available. There is a software Statistica, and we also have Minitab. So Minitab software to conduct to design the experiment basically. any kind of experiment. It can be a simple lathe machining working, or it can be a simple temperature measurement using thermometer, or it can be a simple experiment like the preparation of tea, which we have taken as an example. Any kind of experiment you can design properly by using the suitable factors which are which are independent and which influence the dependent. So two important things we need to remember when you are going for an experiment, that is number of levels, and number of factors. So factors are nothing but the independent variables. In our example, I am just repeating the example. In our example, milk is one of the factor, and sugar, say, another factor. So water, another factor, and processing time means how much time you are heating is also another factor. Just for an example, processing time means how much time you are boiling the tea. Next, what is level means? Actually, you can measure, you can take different levels like 1 cup, 2 cup, 3 cup. It means that, so we have 3 levels. So at first we are using 1 cup of milk, and then 2 cup of milk, and then 3 cup of milk, right? And sugar, say one spoon, 2 spoons, and 3 spoons, right? Water also similarly we can have 3 levels: 1 cup of water, 2 cup of water, and 3 cup of water. Processing time also we can have 10 minutes, 20 minutes, and 30 minutes, right? So if you have the 4 parameters, 4 factors, and 3 levels, then accordingly you can design your experiments and you can perform. So there will be various combinations like 1 cup of milk, 2 spoons of sugar, and 2 glass of water, and 10 minutes, and different combinations like 10 minutes. Okay, so there are some factorial combinations that will automatically design. And finally, what is your solution? The taste. So taste is your y. Okay, and these are x1, x2 up to xk. So if you conduct these experiments, you will get an idea. You will get an idea at which condition you are getting a better taste, right? So the design will gives you a clear idea, like there are 4 factors and 3 levels, right? So 4 into 3 factorial ways you can conduct the experiment, and you can find out which one is giving a best solution among the given solution. So like that, you need to first do the experiments and generate the data, and after that only you can go for the optimization for improving the process and for efficiency of the process and improving the product result, etc. So there are various designs like central composite design and full factorial design, etc. So this is just for an idea I'm telling. So in this particular case study, I have used central composite method in order to do the experiments. Yeah. So let me go to today's present case study. Today's present case study and how I have done the experiments, and how probably how I'm done the optimization, etc. You will get an idea, right? So present case study, I'm dealing with the machine called abrasive flow machining, right? So we worked on abrasive flow machining. So this is one of the one of the machine we generally use for finishing purpose, and it comes under manufacturing related research area under mechanical engineering. Yeah. So even though you are a computer science engineer, okay, when you are doing an interdisciplinary work, when you sit with other engineer, right? Either it can be a mechanical engineer, civil engineer, or electrical engineer. So when your job is to do the optimization, to do machine learning, to feed the mechanism for prediction purpose, you need to know the background, right? You need to understand the background. What is the experimental interest? What is his requirement? And what you need to focus on, and what you need to feed your machine learning algorithm, your model, in order to get the required result, right? So the knowing the background is very important. So that's why I will brief you my background, and then you will understand better. You can correlate better when we discuss the fuzzy model and also the J algorithm model. Yeah. So abrasive flow machining, it's basically consists of two hydraulic cylinders. So we have a hydraulic cylinders, one here, and a hydraulic cylinder two. So these are placed opposite each other, and in between we have a workpiece fixture. We call it as fixture or tooling. So the job of this machine is actually, so we place a workpiece in the fixture. This is our workpiece or sample. So let us call sample. So my job is actually to finish the sample, right? So this is the inset. So inset, you can see that the sample is getting finished by using this abrasives, which are flowed through and through. So my job is to finish this sample, which is placed in between these two hydraulic cylinders, right? And another point here is one tricky point is there, that is the tool which we are choosing. This is the tool, right? So the tool which we are choosing is semi-solid in nature. So it is the combination of viscoelastic polymer mixed with the abrasive particles. So it's the combination of viscoelastic polymer mixed with abrasive particles. It means that the abrasive medium is semi-solid in nature, and it is like a paste. It is like a paste or gel, so that when you pump the medium, when you pump this paste, it can easily travel through the target surface. So that is an advantage. What are the advantages? I'll tell you. Advantage is it can finish the intricate geometry. Okay, it can finish the micro holes. It can finish the micro channels, right? So why? Because it is having a flexible behavior. The media, the paste which we are using is having a flexible behavior. So what is viscoelastic nature, etc.? Just for a simple example, I'll tell you. So every day you like we use toothpaste and we brush our teeth, right? Yeah. So generally the toothpaste is a kind of viscoelastic material, right? You know the behavior of the toothpaste, right? It's like a gel, and sometimes in some toothpaste we have some salt particle present in the toothpaste, right? So just assume that salt particles are something like this sand particles or something. Okay, means the toothpaste is carrying this salt particles, and what happens if you brush it? You brush it, your teeth will become better and you will get shine, right? Similarly, the similar kind of experiment here we are doing actually. We are brushing the workpiece with polymer gel, which is mixed with the sand particles, okay, abrasive particles. And our sample is actually a metal. So we are brushing the material, or we are buffing the material in order to get the shine finishing by pumping the medium to and fro. Yeah, so this is a simple technique. If you see a small video, you will understand what is the specialty of this semi-solid medium I'm talking, and how it can be used for finishing of complex geometries. Yeah. So this is the semi-solid media I'm talking about in my case study, in my work. So this is the mixture of the polymer gel mixed with the abrasive particles. And what is my job? What is the job here is, what is the experiment we are doing here is, we are finishing the manifolds. So manifolds are used in the car engine, right? Automobile engines, and the finishing of internal geometry of these manifolds is important. So this is the tool. So this is the tool we use. This is after finishing and this is before finishing. So this is before finishing and after finishing, and these are the abrasive particles we are using for the experiment. So these are the abrasive particles which are used for scratching, for abrasion purpose in the case study. Like various grades of abrasives are available, so that will become an independent factor. So various grades means, so in the previous case, the size of the abrasive is large pores, right? In this case, it is fine. So there are various grades available. Yeah. Now you can see we are pumping this semi-solid medium by hydraulic pressure. So this is a hydraulic cylinder I'm talking about, right? We are pressurizing the medium to flow through the target surface. So what is the target surface here? My target surface is the manifold, right? You can see the media is coming out from this. So this is my workpiece here. So this is my workpiece, and the tool is coming out from the workpiece by radiusing it, by deburring it, by removing the burrs, and also by finishing the workpiece. Now you can understand, so what, how workpiece is the complex and how the integrate geometry can be finished by using this technique. So here the reused media is again pumping to and flow by using this hydraulic. Yeah. So this is the workpiece, and we are pumping the medium through the target surface. My target is actually to finish the internal geometry of this workpiece. This workpiece is generally used in our car engines or automobile engine. So this process can be used for finishing multiple holes and as well as to radius the complex geometry and also to finish the complex geometry. So this geometry is complex, right? You can't take a grinding machine inside and you can't finish it. Are you following, guys? Are you following? Anyone reply? Yeah. So hope you are following. So we have different tooling to hold the workpiece. So in this case, the workpiece is external, and in this case, the workpiece is internal. And we make fixtures. We make fixtures for finishing internal geometry and as well as external geometry. I'm not getting a reply. Anyone reply? Are you following?
Yes, sir. Yes.
Yeah, fine, fine. Okay. So let me go to the case study now. The various applications of this abrasive flow machining, or we can use in the turbine engine parts, medical implants. So this is one of the important application. So medical implants, there are some surface implants and there are some subsurface implants for on a human body, right? So knee replacement, kneecap replacement, etc. So they generally use titanium alloys, right? So we need high-end finishing of these implants when you are injecting into your human body, right? In that aspect, actually, This finishing is very important. Medical implant finishing, dye polishing applications, automotive components applications, etc. So now you understand a little bit about abrasive flow machining, right? And where we use, what are the applications? I said applications are like automobile component finishing, medical implants, etc. And you understand slightly the technique also. The technique we generally use the semi-solid medium or the flexible medium for finishing the components. And you also slightly understand like how the gel it looks like in the video, etc. Right? So after understanding the basic background, you need to categorize the factors, right? So what are the factors of this particular background for a particular machine? So there are machine settings, abrasive medium settings, and workpiece configuration settings, right? So we need to screen all the factors, identify the factors, and then you need to screen which are important, which factors are affecting the response, and which factors are not affecting the response. So there are some factors like extrusion pressure, right? Extrusion pressure means in the video, if you observe, we are pumping the semi-solid media, we are pressurizing, we are applying certain pressure so that the media is flowing from the workpiece, right? So how much pressure you are applying? So that is important here, extrusion pressure. So number of cycles, flow volume and flow speed, and medium, since the medium is semi-solid, so we need to know the medium viscosity, medium rheology, and as I said, we are adding the abrasive particles or the sand particles, ceramic particles, etc. in mixing. So you need to know the type of the particle you are adding, size of the particle, and the concentration. So what is the concentration of your abrasive with respect to your polymer gel? So that is also important. Either you are adding 50% of abrasives with 50% of polymer gel, or 40% of abrasives with 60%, etc. You need to confirm. You need to confirm by doing some pilot experimentations and accordingly. Workpiece configuration, like we have restricting passage length and area, and the workpiece hardness also will play an important role in fixing the parameters. Yeah. So there are some advantages of the process which I have shown you, and there are also some disadvantages. Advantages are like it can finish the complex geometries and it can finish the medical implants, etc. Limitations are low material removal rate and low finishing rate, right? It means it is taking a lot of time to finish the required component. Like in machine learning, we combine two processes such as fuzzy and ANN, right? And we call it as ANFIS. And we combine ANN and other processes, and we call it as hybrid parameters, hybrid processes. So such kind of theory also applied here. So we hybridize the process. So we hybridize the process by adding the additional mechanism in order to get more finishing and in order to finish the advanced materials, etc. Quickly, I will go to my process. Yeah. The process is simple. So abrasive flow machining, we are pumping the media to and fro to get the finishing required. And the hybridization, in order to do the hybridization, actually we are adding the actuator. We are adding the actuator which is vibrating the workpiece from outside. So this we call it as piezo actuator. So we are giving certain vibrations to the workpiece externally. So this is an additional mechanism we are adding, and due to this additional mechanism we are adding to the simple process, we can call it as a hybrid process. So this attachment, we have an amplifier, computer, offset, etc. So this is the technique. Just an idea you can see. So we are pumping the medium. So this is the semi-solid medium, semi-solid medium, and this is my workpiece here. So this cylindrical bush is workpiece. Yeah, and here you can see we are vibrating. We are vibrating the workpiece by using the attachment. Why we are vibrating is actually for getting an additional advantage. We are vibrating the workpiece. And what is my target? To finish the internal geometry of this cylinder, right? So the process is new here. So the process is new. So as I said, research can be done in two different factors. One is the process should be new, and also the product. Either you are developing a new product or you are you are improving the existing process and developing a new technology, right? Already the existing process is the simple abrasive flow machining, and whereas when you are vibrating the workpiece, we are hybridizing the process, and that comes to a new technology in a field. So this is the original machine you can see. So this is a DC offset. This is the amplifier. So this is the machine we have. So this is an actuator, and here we are vibrating. This is a semi-solid media I'm talking about, and you can see here the hydraulic cylinders were pumping the medium to and fro for finishing the required workpiece. Yeah, just for an idea. I'll skip the principles. This much detail in deep is not required for our today's lecture. I'm just skipping. Yeah, our area of interest is the experiments, how we conducted the experiment, and how we have gone for the optimization by using fuzzy logic and J algorithm. Yeah. So based on the experimental setup which I have shown, so we have designed three different phases of experiments, say phase 1, phase 2, and phase 3. So in the phase 1, actually we have finished the internal surfaces by using radial mode. So we have an adjustment of actuator in radial mode and axial mode. So in the phase 1, we have used radial mode, and in the phase 2, we have adjusted to axial mode, and phase 3, we have finished the external surfaces, right? So we planned three different phases of experiments, and in these three different phases of experiments, in the first two phases, we finished internal surfaces, and in the third phase, we finished external surfaces. And this is the experimental setup used. Yeah, these are the work pieces. So for internal finishing, we used this aluminum bushes. So the target is to finish the internal geometry of the aluminum bush, and we also used ENA examples. For external finishing, so we have used these gears. So we all know about gears. So what is gear? Bevel gear. We have different types of gears like bevel gears, spur gears, etc. So gears are generally used to transmit motion from one shaft to another shaft, right? So generally these bevel gears are generally used to transmit the motion for a perpendicular shafts. So these gears, gearbox, etc. you will find out in the automobiles or in the lathe automobiles which you are using, or in the lathe machine, etc. You will find out the set of gears, etc. So my job is here to finish the gear. So why we are finishing the gear means to improve the functionality and to improve the life of the gear, right? Functionality and as well as the life of the gear. So there are some parts, if you observe, so you are using a bike, right? You are using a bike. There are some parts which are exposed to fatigue loading, right? Which are exposed to environmental conditions, some metal parts, right? So due to that, actually, there is a chance of getting corroded, right? And there is a chance of getting failure, surface failure, etc. To avoid them, actually, we go for high-end finishing. We go for nano level finishing, micro level finishing, etc. So that when these are subjected to fatigue loading, when these are exposed to environmental condition, then also they will give, these parts will give more life, and the life can be increased for your automobile company, just for an example. Yeah. So these are the workpieces taken in the case study. These are the workpieces taken in the case study, and this is the semi-solid medium prepared in the laboratory scale. So we have used 150 mesh size, 200 mesh size, 300 mesh size, 400 mesh size, etc. And these are the composition, chemical composition of the samples, workpieces used. And you can see these are various formulae used to determine the responses. So we have two responses, that is surface finish and MRR, and these are generally used for the design of experiment. Yeah. So finding out the levels and parameters, I have discussed an example for a tea, cup of tea. Similarly, Here, in my particular experiments, I have identified 4 independent parameters. So that is applied frequency A, we code it as A, extrusion pressure, we code it as B, abrasive mesh size C, and processing time D. And based on the literature and as well as the experimental conditions, we have certain levels like applied frequency can be varied from 0 to 20 kilohertz. Okay, extrusion pressure can be varied from 2 to 22 bar Pascal, right? Mesh size can be varied 150 to 300. Processing time means how much time you are machining. That can be varied from 4 to 8. So these are fixed before going to the experiment. So this knowledge, this fixing data, generally you can do by pilot experimentation or you can inspire, get some data from the literature. And there are some constant parameters like which doesn't have much effect, like media flow rate, viscosity, abrasive concentration, temperature, initial roughness, amplitude, etc. So these are, we are not varying this, but we are varying these parameters. And what is your y? Y is means the objective function, the your result, that is improvement in surface finish, that is maximum the better, and material removal rate, that is again maximum the better. So you need to choose the number of parameters and levels and the constant parameters, and you need to also choose your responses, what kind of responses you are expecting based on your result. So these are my parameters and their ranges. Next, design of experiment will gives you design by getting more information with less number of experiments. I think approximate some 31 experiments are conducted to find out the required surface finish and MRR. Yeah. So here, as I said, there are 5 levels for each parameter. It means we are varying from A is 0 to 20. It means that you will have experiment at 0. Okay, you can see one experiment at 0, and you will have an experiment at 5. Okay, it means that at 0 frequency, at 5 frequency, what is the result? And you will have an experiment at 10, you will have an experiment at 15, and you will have an experiment at 20, right? And there are some combinations. So B range is also from 0 to 22. C range is say 150 to 350. So, okay, and D is from 4 to 8 minutes. Yeah. So what is understanding here is, after doing this particular set of experiment, what are the observations are? Okay, at 15 frequency, you can see this particular result. At 15 frequency, 7 bar of pressure and 200 mesh size and 7 minutes of processing time, I am getting 77.34% of surface finish and 14.51 milligrams of material removal rate. So, is it a best solution? So, if you see all the experiments, I find my delta RA means my surface finish improvement is should be maximum the better, right? So according to my understanding, this is the best solution. So 80% of improvement is my best solution, right? Why? Because my response is higher the better. Next is material removal rate. This also my response is higher the better. And in this case, my best solution is 14.51. Yeah. So now actually, in order to get the best MRR, you can choose this particular parameters like A15, B7, C200, and D7. Whereas in order to get the best delta RA, you can choose 15, 7, 300 mesh size and 7 processing time. right? But my doubt is, whatever whatever the data obtained is well and good, but I have struck with two questions. My first question is how to get the best solution for both objectives. Means how to get my delta RA maximum the better, and how to get my MR milligrams also maximum the better. At what conditions I will get maximum the doubt. And the second doubt is actually here we varied 5 levels. Say for example, 0 to 20 means 0 we have an experiment, at 5 we have an experiment, and at 10 we have an experiment, at 15 we have an experiment, and at 20 also we have experiment. It means 5 levels. So 1, 2, 3, 4, 5. So 5 levels, 4 parameters we have varied. Now my question is, what happens if the frequency is in between this range? So if the frequency is 3, then I don't have an experiment. Okay, if the frequency is say 7, I don't have an experiment. If the frequency is say 13, I don't have an experiment. If the frequency says some 17. So this is with respect to A, right? I don't have an experiment. But if I want to repeat the experiment, then it takes a lot of time and lot of money is involved. So I can go for a regression model development, right? Or I can go for a fuzzy model development, etc., in order to predict the data, in order to get the results within the range or slightly extending the range, etc., right? And also I required a multi-objective optimization in order to get the best solution for both parameters, and also to find out the best solution individually also. So I need to go for an optimization once after getting this data, this set of results. So let us see some analysis of these results. So we have two regression models. So this regression models we call it as objective functions. So these are objective functions. So this is my response 1 and this is my response 2. So objective function 1, say f of x 1, f of x 2, right? So two objective functions have a regression equations generated with respect to error, with respect to the design error, which is not under control of the experimenter, right? So this objective function gives you the coding values, means minus 3.75 into A. What is A here? A is our applied frequency. B is extrusion pressure, which we applied in the experiment. C is the mesh size, and the D is the processing time. So the equations are generated with the coded values. So what we can do is actually you can insert the unknown values of our A, B, C, D, and you can generate and you can get the result of the experiments which are not done, and you can check the predicted value. You can check the error by comparing the experimental value and the predicted value. So that is one method. Yeah. Next another method is you can go for using the fuzzy logic, etc., and J algorithm for doing the required optimization. Before going to that, so the set of experiment will gives you the independent effect and also the interaction effect. So this slide shows you the independent effect. So this is our parameter A, which is my first parameter, and this is my response 1, right? Response 1. So we have a curvature. We have a curvature based on the experiment. So that is like it is slightly increasing and slowly it is settling down, right? So on the x-axis you can see here the applied frequency is varied from 0 to 5, 5 to 10, 10 to 15, 15 to 20, etc. And the improvement maximum is a minimum is this and the maximum is this. So that data we can get. So similarly, The extrusion pressure also is following certain trend, and the abrasive size is also following certain trend, and the processing time is also following a trend, right? So these four are the parameters which we are varying, and this is my response one. So similarly, when you talk about the interaction effects, so what is the interaction of two parameters on the result? Like in the graph, you can see one is applied frequency and the extrusion pressure. So what is your interaction? What is your interaction, and how these two, when these two are interacted, then what is your response? One R1, how it is affected. Similarly, applied frequency and abrasive size. So what is the interaction and how it is showing the result, right? So applied frequency with processing time. So how it is interacting. Extrusion pressure, abrasive mesh size. So how it is interacting. So these are the combined effects. So the combination of parameters and how they are going to affect. So again, this is my response to. So response to also have generated the NF data. So this is my response to, that is material removal rate. So it is increasing and slowly it is getting saturated, right? So similarly, extrusion pressure, we have data for response to. Abrasive mesh size, we have some data, and processing time also we have certain data generated, right? And these are again for response to how the interaction plots, how the interaction plots are there, like for when we are combining two parameters, then how the your result is adding, how your results is behaving, right? So that's what we can see from these interaction plots. And these are some results, experimental results for means for linking this data or for the validation of the experimental data. Yeah. So coming to our prediction model, the fuzzy model. So how we apply the fuzzy model and how we feed the fuzzy model and how the results are compared with the existing regression model, and how the fuzzy model prediction is useful for the further research, etc. That we'll discuss now. So we used a simple basic fuzzy model, fuzzification by using a simple MATLAB tool, by using MATLAB, etc. We use the fuzzy model. So the first important thing in the fuzzy model is to create your parameters or the factors. So these are my factors. So I know my factors and I also know my levels of my factors. And then also you define your responses. So these are the dependent parameters, or we can simply call as responses, either y or f of x, etc. So these are my responses, R1, response 1 and R2. Okay. So first step is you give the low level, medium level and high level to your membership functions. You create the membership functions for A, B, C, D. So ultrasonic frequency is my A, extrusion pressure is B, abrasive size is C, and processing time is D. And what are the levels we consider in the experiment? We considered 0 to 20. Okay, 22 to 2 to 22. So this is A, this is B, right? So when you're creating a membership function by using a fuzzy model, you can slightly stretch your membership functions. So this is my low level, this is my medium level, and this is high level. So up to 25 we have stretched our parameter A, and here you can see some -5 to 25 we have stretched our parameter B, and up to 400 we stretched our parameter C, and the other side 100. Means the in experimental we have chosen only 150 to 350, whereas in the membership function we stretched the band from 100 to 400 mesh size. Yeah. So processing time also similarly we stretched from 2 to 10. So actually in the experiment we have used from 4 to 8 only, 4 to 8 minutes. So you can slightly stretch the band to get more prediction, of the values which are not taken in the experiment. So these are the membership functions: ultrasonic frequency, extrusion pressure, and abrasive mesh size, and the processing time. So these are the functions. And now you can also stretch your, you can also create your membership function for the response one. So this is R1 and this is R2. So here also we are slightly stretching. So since R1 is the maximum, the better. So the result can be from 0 to 100, right? And R2 is also the maximum, the better. The result can be some 0 to 20 or 25. Not more than that we can go for this particular lateral removal rate. Yeah. So here we are giving a lower level RA, medium level RA, and higher level RA. So how we are deciding this? So these levels are decided based on the experimental data only. So the experimental data which we obtain will gives you an idea. So what is the low level? Okay. What is the high level? What is the medium level? For example, so this is the high level for response 1, right? 80.12 is the high level. Okay, and 26.12 is the low level. And say 30 or 40 will be the medium level, just for an example. So we need to understand the trend of the responses based on our experimental result only, right? So similarly for the response 2, the highest value will be this one, okay, and the medium value say 11 or 12, say the medium, and the lowest value say 9.81 or 9.12 will be the lowest value, and 8.62 is the lowest value. So we can stretch the bands, create the membership functions according to the given data. Yeah. So next step is create a simulation block for fuzzy logic model. So, and this is the fuzzy logic controller. So we have created the model, fuzzy logic model, and we have input, we are giving the input to fuzzy logic controller. Means we need to feed this fuzzy logic controller in order to predict these results. So that is my response 1 and response 2. Now how to feed this fuzzy logic controller? I will show you one result. So in this particular result, you can get, you can say for example, if A is 17, which is not done in the experiment, B is 19, C is 400. So B is 19 also not done in the experiment. C is 14, D is 9, and sir, it is predicting the surface finish, and also it is predicting the material removal rate, right? And similarly here, when A is 3, B is 5, C is 800, and D is 3. So it is predicting some result here. So that is 34.03 is your surface finish, 10.54 is your MRR. Means this experiment is also not done before. So we are feeding the controller, fuzzy logic controller. So now how to feed this fuzzy logic controller? So we use AND OR rules, okay, AND OR rules based on our developed experimental data. Just for an example, so say for example, we have 31 experiments data and 4 parameters, 3 levels, right? Sorry, 4 parameters, 5 levels. So 5 into 3 factorial ways, actually we can write the rules. I will tell you a small example. I will tell you how to write the example, etc. Sorry, rules, etc. Under rules to feed the fuzzy logic controller. Take the first experiment. A is 15. So in my membership function, if A is 15, it lies at high. So when A is high and B is 17, so it lies under again high. Yeah. So when B is 17 lies under high in my higher level in my membership function. When C is 300, 300 lies in medium in my membership functions, and D is 5. D is 5 also lies in medium, right? Then this 65.36 is already obtained result, right? So this 65 actually lies in medium in my output. 11.56 is also lies in medium. Now, what is the rule is when A is high, B is high, C is medium, and D is medium, then your predicted result will be in the medium band. So that is the rule. Okay, the predicted result R1 is in the medium band, and also the predicted result in the R2 also will be in the medium range. Let us take another rule. So when A is high at this particular case and B is low, so the your pressure is low, and C is also low because we are using 200 here, 200 less size, and D is high, so we are using a little high, more processing time, right? So 7 minutes. Then the output prediction rule is the obtained R1 will be high and the obtained R2 also will be high. So the rule is like that. So if your A is high, B is low, C is low, and D is high, then your obtained output also will be high. And when your obtained output R2 also will be high. Similarly, you need to write the number of rules, factorial ways of rules for your experimental data, and you need to feed the fuzzy logic controller, right? So you can feed the fuzzy logic controller, and after that the fuzzy logic controller will generate the values according to your inputs. So these are my inputs in the fuzzy logic controller, and these are my outputs, right? So here I am not doing any experiment, but I am getting the output directly after feeding the fuzzy logic controller. But how to validate them? So in order to validate them, actually we have done some 5 confirmation experiments. So these 1, 2, 3, 5. So these are the confirmation experiments we have done. Means we have re-verified by doing the experiment. So and we check the error, and also we compared this with the regression analysis. So here you can see when A is 3, B is 5, C is 800, and D is 3. Then experimentally my output is showing 36.78, whereas my fuzzy logic showing without any experiment, it is showing 34.03. In the another case, when A is 7, B is 9, C is 220, and D is 7, my experimental value after doing lot of after spending lot of time and money, I am getting 55.21 improvement. But simply by using the fuzzy logic, I am getting 56.48, so which is very closer. Similarly, you can see the third experiment I am getting 62.21 finishing, and in the fuzzy logic I am getting 63.41, and in the fourth case you can see 73.39, 72.19, 70.34, 69.24. And if you compare the error, right? So these are the error percentage: 1.74, 3.08, 5.03, 3.58. And in the first output, the error is 7, 2%, 1%, 1.63. How the error is calculated is generally like it is just you need to calculate the experimental result and the predicted result, and you can find out the error. So initial value minus final divided by initial into 100 will get the error in the percentage, right? So after understanding this, after understanding the experimental value and the fuzzy model developed, so you can see how values are closer. So this dotted portion shows the fuzzy model, okay, and the thick line, green color line shows the experimental model. So you can see how results are close and how the prediction model is very close to the obtained experimental result. So similarly, we have tried the fuzzy model and the response surface methodology by changing the axial mode, and also by generating the results by changing the axial mode of the vibrations, and at what conditions it is giving better, etc., and optimizing them properly for the next experimental set. So this I am skipping, and I am going to another algorithm, that is Jaya algorithm. So how we apply J algorithm and what is the purpose of this algorithm, etc. As I said, in order to find out the multi-objective optimization and as well as the best solution, we go for advanced algorithms. And J algorithm is one of the advanced algorithm I can say. So Professor Rao has developed J algorithm in 2011 for solving both unconstrained and constrained problems. J technique is used with the help of MATLAB. So coding is also available. I will show you the coding also. So after the application of GA to the objective function, the optimum parameters and their levels are to be noted. Yeah. So how the J algorithm steps etc. will come. Let's start. Define the population size, number of variables, and termination principle. Next, define best solution and worst solution and evaluate them. Right? Means you need to define your best solution in your case study and the worst solution in the case study. And the code comes like this, right? So here x dash j k1 is nothing but actually new value. So if you decode them, new value is equal to old value plus random number. So it takes a random number into best value. Best value means for your experiment, which one is best. So in my case, maximum the better. So 80% improvement was the better, right? Best value minus of old value minus random value. So this is the random value and worst value. So worst solution minus of old value, right? So this is the old value. So this is old. So this is the worst solution. So this is the random value. So this is old. So this is the best solution. This is the random value R1 and this is again old. So in order to get the new value, so this code is given. So this code is given in order to actually to take far away your worst solution. So the equation is written in such a manner that you should obtain the best solution and you should get away from the worst solution. So the equation is written in such a way. And the next step is, if your new value is greater than old value, if yes, then replace early solution, and if no, then keep early solution. Next is the termination principle fulfilled. If yes, then print the optimum solution, and if no, the loop will repeats. Right? So this is the simple J algorithm. So the main the main objective of algorithm is to get the best solution and to make the worst solution also comparatively better. So in detail, if you see the algorithm flow chart, so here you can see start, define population size, number of variables, and the termination criteria. And population size, number of variables are given. Then you find out f of x. So f of x is nothing but here our objective functions. You need to define the objective functions and best and worst solution, and then you go for the equation. So this generally for MOJ, I will explain you when I'm explaining the results. Yeah. Yeah. So what actually the tool does is, once after doing the simulation, what it actually does is, are you able to see my Excel sheet? Anyone reply? Yeah. So after giving the initial population, So the A, B, C, D are my process parameters and f of x is my objective, right? So the algorithm will takes you to how to function, means algorithm will takes you to the initial population, and then basically it find out the f of x, means your objective function, and from that it will finds you your best solution according to your input given in the coding and your worst solution. So in this case, my lower the value is my best solution and higher value is my worst solution. So in the next generation here you can see in the next generation, so your worst value is 0.63 and your first worst value is 0.72, means your worst value is also getting improved. So, and what is your best solution? Best solution is 0.011. So after like it will continue the loop, and finally it will gives you the best solution for a described for a given set of parameters. So that is 0.00942 percentage of improvement in the surface finish, and the worst solution is 0.277, means the worst solution is also step by step decreased. And what are the final outputs? What is the best solution and what are the final outputs, etc., for getting this, and what are the A, B, C, D values? So A, B, C, D values we need to use for getting the best solution, etc. So similarly for MR, for the second response also here you can see. So in the initial loop, it will find out which one is best. Say for example here, higher the better is best, and lower value is worst. Okay, and slowly it will take some generations with less computational time. It will slowly goes to the best solution. So here the best solution in the second generation is 15.38, whereas in the first solution is 13.68. In the first generation, worst solution is 5.8, whereas in the second generation it is 7.9, means 7.9 is high. So as per the loop, actually it will continue and it will replace the required worst solution and it will continue the loop. So your best ABCD are A, B, C, D, means at 20 kilohertz frequency and at 2 extrusion pressure, 150 mesh size and 8 minutes of processing time, you are getting some 19.1183 milligrams of material to mole. So that is what your output, that's what your targeted output. When you go for MOJ, means that when you are adding two parameters, two equations, two objective functions, then also we can find out the method is same. So you can find out the best solution among that. So your best solution is at 20 kilohertz frequency and 2 bars of pressure and 350 abrasive size and 8 minutes, you are getting a best solution. So when you are doing the multi-objective criteria, then one important thing is you have to give the weights. So after writing an objective function, you have to give the required weights to the are you able to see my PPT?
Yes, sir.
Yeah. So at say for example, this is the convergence result of my first output, that is response 1. So once after getting converged, actually you can stop the solution. So these are the conversation for response 2, material removed. And when you're doing a MOJ, actually you can give the weights. MOJ means actually, for example, my response 1 equation is say y is equal to f of x1. So maximum the better. Response to equation is y is equal to f of x2 up to xz. Okay, you need to combine these two equations according to their maximum functions and minimum function, etc. So that combined equation will be inputted in the coding, and accordingly you need to give the weightage to R1 and R2. Means 0.5 times you can multiply the R1, 0.5 times you can multiply the R2 in the equation. Similarly, 0.6 weightage you can give to the R1 and 0.4 to the R2, 0.7 and 0.3, 0.8 and 0.2, 0.9 and 0.1. Like that. Similarly, you can try the various weights. You can give the various weights, and A, B, C, D are randomly generated, and f of x is also generated based on your coding, and the surface finish and MRR are generated, and accordingly you can go for your roughness and MRR achieved for this particular results, right? So similarly, we have worked on magnetic abrasive finishing also. So the first important thing is the finding. Say for example, if I'll show you a small basic setup, right? So simple setup you can see in the. So in this particular video, actually, you can see the rotation of the tool, and you can see the plate, which is the workpiece here, right? And there are some abrasives, and our job is actually to finish this particular plate, right? So there are some parameters acting here, the rotation speed of the tool, okay, and the abrasive size we are using. And since it is a magnetic abrasive process, so the magnetic flux density using in this particular experiment, etc. No? Right? This small setup is generated. This small setup is developed to finish the workpiece, etc. And the idea is actually how you validate the results and how you predict the results and how you perform the experiments. So that is what important. So here the the parameters and the ranges are fixed. So there are three parameters there: the speed of the electromagnet, voltage, and the abrasives. And there are three levels chosen for a video which I have shown, that setups for the small setup. And we have generated the experiments, and based on that experiments, actually J algorithm is used. J algorithm is used. Again, the regression, the generations are converged, and again the results are compared with genetic algorithm, etc. And you can see here at 30 C1, that C1 is the parameter here, and at 50 RPM, sorry, 500 RPM, and at 50 C3 of the parameter, we are getting the predicted result and the actual result, and also we compared the results with the genetic algorithm. So the scope of the presented work is actually, we have a lot of scope to do the prediction, and we have a lot of scope to do the optimization of the manufacturing processes. And I will show you some interesting articles which are published based on the data which I have explained here. Say for example, finishing related paper, right? So J algorithm on nano finishing. So I think I need to share this. Share content. Yeah. So if you see the paper, so this paper talks about the new algorithm, new optimization algorithm or parameter optimization of nano finishing. So whatever the method we discussed related to nano finishing. So in this paper, actually, you can see the J algorithm code. So how the new values are generated and how the worst values are neglected and given priority to the best solution. And you can see the algorithm, how the algorithm step by step is calculated, and you can also see the objective functions, right? So these are the objective functions which are directly sometimes taken from the experimental data and sometimes directly from the journal papers. So these are the objective functions RA, and 40 lesser than or equal to B lesser than or equal to 85. These are the levels. These are the ranges, right? So 40 to 85 is the ranges they varied in the experiment, right? And like that, they have collected the data related to finishing methods, and these are the optimum combinations they have developed, right? So by using J algorithm, actually, these are the results they found, and the computational time is given here. RA and MR, the surface finish and material removal rate. And what are the parameters? VU, C, DN, these are the coded values. So at 80, 85V, 45C, and 100D, and N, if N is equal to 20, then your roughness is 0.53 and your MRR is 0.73. So in this case, actually, say for example, RA is micrometer, lower the better. So 0.4 is the better value, and MRR is higher the better. 0.738 milligrams per minute is the higher the better, and the computational time is also recorded. And in the next table here, you can see the genetic. It is compared. The J algorithm is compared with genetic algorithm, right? And you can observe that the results obtained from J algorithm are slightly better when compared to genetic algorithm, right? And of course, if you compare the computational time also, like you can say J algorithm is giving the better result in slightly better than genetic algorithm. So at this particular stage, he got 0.417 RA, whereas 0.4 in genetic algorithm. So like that, there are some converged graph results at what generation the results are converged, and there are and they have solved various problems, all finishing related, nano finishing related problems in this particular journal. You can go through them. You can go through them, and the explanation is also given. Explanation is also given in some journals. I will show you. So before going to explanation, actually the coding is directly available. I will share the content. I think you should be able to see the paper. So the codes of J algorithm and its variants. So already the code is available. Only thing is actually you need to change your variables, and you need to insert your required best solution, worst solution, and also your f of x. Your objective function is need to be inserted properly, and your ranges and the parameters are need to be given. The code is already generated and the logic is already feeded, and that code is already available on websites, on internet, right? So only thing is you need to change your f of x, your objective function, and as well as your levels, your parameters, ranges, etc. You need to change. So there are various multiple applications, and there are this, since this is an interdisciplinary work, so I will show you some thermal science application where the papers are published, and you can also see some electrical engineering applications where these papers are applied, etc. So let us see thermal application paper. Yeah, so if you take this thermal science application paper, so here you can see thermal performance optimization of the underground power cable system by using a modified J algorithm, right? It means that the J algorithm is slightly modified so to get the better best solution. So in this particular paper is for the thermal applications, and at the end of the paper actually like you can see the conclusions, and as well as in some paper we have given the explanation also how the generations are made, etc. So MO Jaya on machining. So multi-objective Jaya and machining related areas. So you can see this particular paper. Yeah. So engineering applications of artificial intelligence. So the journal name is Engineering Applications of Artificial Intelligence, the multi-objective algorithm for optimization of modern machining processes. So in this particular paper, so they have used Jaya algorithm and they have optimized different types of modern machining processes which are published in the data, and that details are directly taken here. Here you can see maximum CV is the maximization function and minimum RA. Minimum RA means the RA required is minimum. So these are equation 9 and 10 are the objective functions and the parameters levels are given here. So various parameters which are varied are given with the ranges here. So these equations, the maximum minimum equation is written in order to find out the MOJA, and here you can see the results, right? So we are finding the best solution, worst solution, and we are neglecting the worst solution and going for a best solution, and we are comparing the results also with genetic algorithm, etc. Right? So you can find out the convergence graphs, you can find out the computational time, and you can also find out how the results are explained, compared, etc. And in this particular paper, one more application is like they have in the appendix they have explained the theory. Yeah. So the demonstration of the working of J algorithm. So this demonstration is given in a clear manner, like how the code is generated and how the random number is generated, how the new value is calculated, etc. Right? So in the table 1 initial population, so first we need to give x1, x2 values that are randomly taken within the ranges. x1, x2 are our variables and f is our output variable. x1, x2 are the input variables. So you need to find out the worst solution and best solution, right? So worst solution is 57. It means that maximum is the worst, minimum is the better in this particular case. So 11.39. So according to the code, what happens? Step by step it is given. So in the table 2, you will find out the means the step will repeats, and among this table 1 and table 2 means table A1 and A2, it will take the best solution and worst solution. It means the best solution after first generation of the first generation is 2.10, whereas worst solution is 36.78. It means, so your worst solution is 57, and then in the second generation it is 36, right? It will replace, means it will take the lower value and then replace the old value, and then slightly it will reduce the worst value. So step by step explanation, after finally you can get the convergence of the results and the best solution and worst solution. Since the in the particular demonstration the lower is the best, right? So 0.21 is the best result for a given example, and worst solution is 24. 24.79 is the worst solution for a given study. So worst solution is the maximum worst one, means the maximum value in the given table. What J algorithm actually does is, if you go to the before iteration, the worst solution here is again 24, and if you go to the before one, it is 26. So it will take the lowest value. It will take the lowest value among the obtained two values. So this is about few challenges in the J algorithm. I will show you one more paper. So that is related to, yeah, okay. Anyway, are you following, guys? Chaitanya? Hello. Hello.
Yeah, dear participants, the session was completed. Thank you, sir. Thank you, Venkatesh Garu, for sparing your time and sharing your knowledge with us, sir. Dear participants, if you have any sort of doubt, you can unmute your mic, please.
Hello.
Yes, sir, it is audible, sir. Yeah, dear participants, if you have any doubt, you can unmute your mic.
You can ask if any queries.
Sir.
You can ask. Otherwise, you can mail me.
Okay, sir, sure, sir. Thank you, sir. Thank you very much, sir.